Thank you. And thank you for the organizers to give me the opportunity to talk about Sylvia weekend. All right, so I think of the first third of the talk, I will talk about the Sylvia's mathematical family because her grandparents and her parent, they are prominent mathematicians I want to talk about. And then something about her PhD student very quickly. Then I'm going to talk about, I pick one topic, which is about the prime ideal structures over the new theorem rings. So that's the topic I'm going to focus on. Okay, so here is the family tree. On this side, we have Sylvia's advisors, Laurence Young, from the he got his degree from the University of Illinois at Urbana-Champaign in 1961, and then above that's Irving Rainer from Cornell, and then Leonardo Eugene Dixon from University of Chicago, 1896, and so on. So when you go up, this is a different Newton, but there's another advisor somewhere above. It has dual advisors, and one of the advisors direct to up to Euler. So that is, yeah, another branch, right? So that is the top. And then here, Sylvia has so far 6 PhD students. Unfortunately, to be the first one, and by age or by academic age, I'm the oldest sister of all of these sisters. All of her students are women students. So we have these 6 people. That's her graduate student. I want to talk about the her grandparents. This is the picture of Grace Chisholm Young, and her grandfather. This is William Henry Young, and these two, both of them are very famous mathematicians at their years. And then below this is their product. It's Sylvia's father, Laurence Chisholm Young, and he also is a well-known mathematician. So these are very 3 famous mathematicians directly in her family. I think you can see the genes of mathematics genes she obtained. So at a very young age, Sylvia started to like play puzzles and do math problems. I think she got all of these mathematics genes from them. All right. First, I want to talk about Grace Chisholm Young. She is an English mathematician. These are the years she died, 1944, during the World War II. And she got her undergraduate degree in Girton College, England, and then she got her graduate work done in Göttingen University in Germany, which is at that time was the world center of mathematics, right? And the most well-known, the most known thing about her is she is kind of a pioneer woman at her time in a discipline like mathematics or science with significant barriers to entry. And I want to, here, I just put this up. She is the first person to obtain a first-class degree at both Oxford and Cambridge University in any subject. So when she took the test, she outperformed all of the boys in the school. And she also, this is the most well-known, she was the first woman awarded to doctorate in any field in Germany. That was in 1895 under the famous mathematician Felix Klein. And her thesis is about the abelian group of something with trigonometry. I don't have space to put the whole thing here. And then later, she wrote papers with her husband. She got an award for this Gamble Prize for mathematics by Girton College for her work on calculus. she also, I was trying so hard to find this fact. I know it was somewhere. She was the first woman admitted to the Royal Society of England in March 22, 1945, and that was a historical day for the society. Actually, in 1995, the same day, the Royal Society had a big celebration for the 50 years of this happening, right? I think they encouraged many women to do math, and also from her success, I think it make more smooth for women mathematicians to go up to either get a job or get a degree. And she wrote actually a lot of papers with her husband, but there are 18 of them are on her own name. So at the beginning, she always had the drawing paper with William Henry Chisholm Young, William Henry. And her there's one theorem named by her name. It's called the Danjoy-Young-Sachs theorem. Okay, that was one of her major contributions. And about her personal life, she married William Henry Young in 1896. Then in 1 year, she started to have children. So within 9 years, she had 6 children. And Sylvia's father was the 5th child of them. But here, please look at this. He just had never had an academic job, because at those years, there's no such jobs for women with doctoral degrees. So she has done all the work at home, and when she raised the children, she wrote mathematics papers. And actually, William Henry Young was out of town many times, traveling a lot. So she had to take care of the 6 children, and at the same time, she wrote a lot of papers. This picture is a picture of the London's Mathematics Club, and you can see it, Grace Chisholm Young, also surrounded by, yeah. Yeah.
People might be interested. It's actually the Mathematics Club of Göttingen.
Oh, Göttingen. Okay. Actually, under this picture, when I got it, it said Division of Laurel. So I don't know what is that. That's what I will ask you about. What's really Göttingen? Okay. Good. Okay, so it's a Göttingen's math. Yeah, so this should be Göttingen, right? Okay, I'll make the correction. So she was there, surrounded by all women. Yeah, there are some famous guys. Yeah. Okay. And now William Henry Young, he also is a English mathematician, and here is his education from Cambridge, and he's a fellow of the Royal Society, president of the London Mathematics Society for those years, and he was awarded the De Morgan Medal of London Mathematics Society in 1917, and also the Sylvester Medal of the Royal Society in 1928. Also, he was the president. He was the president. He was the president of the International Mathematical Union from 1929 to 1936. And here are his major contributions, like Young's inequality for products, Young's convolution inequalities, and there's another thing about inequality, and Young's theorem. He published 214 papers and 4 books, but people are saying a lot of them were jointly with Grace Chisholm Young. With her name also. And someone said Grace has had more depth in writing those papers. So, but only 18 came out on her name. Here is Laurence Young, Sylvia's father. He was born in Göttingen, Germany, and he was the professor and the department head at the University of Cape Town, South Africa. I was wondering why there. Yeah, and I think that was during the war, so that was, they want to move out of England. And then he came to the United States to be, then he has been the professor at the University of Wisconsin-Madison for this many years. He retired in 1975. But I do want to mention some fact later. He's not here yet. He had received this honorary doctorate from the University of Paris Dauphine in 1984. And yeah, this is the one thing I want to mention, that after retirement, he came to Brazil many times, since we are here, to teach students at the University of Campinas.
He was a permanent?
No, just visit. Like a few months each time, right? Yeah. So for many years, I think so after 1975, and he died in 2000. Yeah, so many years he had been doing that. And unfortunately, Sylvia never got to Brazil during that time when he was here. But I think you are following his steps now. You are retired and also come to Brazil. So that's Sylvia's father. He is also a very accomplished pianist, piano player, and a chess grandmaster. Has won a national competition once. And he was known for his contributions in Marrow theory, calculus of variations, optimal control theory, and potential theory. Okay, and there's theorems named by his name. So these are the parents, grandparents of Sylvia. Now it comes to Sylvia. Of course, she was born in Cape Town, South Africa, and the daughter of the 6 children of Laurence Young. She, I think so. Is that right? Margaret. But why is Margaret? Okay. Oh, okay. And she is one of the granddaughter of Grace Chisholm Young and William Henry Young. So they have 15 grandchildren. And her undergraduate education is at the Brian Mao College. And I mentioned before, her PhD thesis from is down in Wisconsin. This is her doctoral thesis, the title. I'm not going to touch that. And of course, this is advisor. And here I list some of her titles. And amazingly, she also was an NSF graduate fellow. And now she's a fellow of AMS, and she's the fellow of the first group of AWM. And she was she's the past president of AWM, and she was the president in 1997 to 1990. And she joined the University of Nebraska Lincoln as faculty in 1972, 1 year after her doctorate degree. And in 1987, she was named full professor. And here I want to then talk about Sylvia's new theorem, the research work. I focus on the new theorem part. So new theorem research. First of all, just very, very quickly touch her doctoral thesis. It's also has new theorem in it. So if you consider a commutative new theorem ring and R and R module M, here is a theorem from the first part of her thesis. Let M prime be an essential extension of M, if every homomorphism phi from an ideal I of R to M can be extended to this another homomorphism from R to M prime, then this M prime is the injective Hall of M. Another, the second part of her thesis is on some conditions on M, so that this tensor product equal to 0 for some finite times. That's about her thesis very quickly. And then now I will talk about the prime ideals in this Euclidean rings, which is one major a main project of her research series. These are the collaborators on this project. Did I miss anything? Anyone? I look at all of the papers. So, yeah, that's it. And all of your PhD students. So here is the, when we consider a commutative Newtonian ring R, the spectrum is defined to be the set of all prime ideals of R, and that forms a partially ordered set, and we call it the pole set with the inclusion relation. The question is, what is the structure of this pole set? And there's a big question about the pole set. So here, let me just quickly give you the notation. Spec, that's what I just mentioned, the set of prime ideals of R. And we talk about, for a prime ideal P, the height is the length of maximal chain to P from a minimum prime. And then the dimension is the maximum of all of the heights. And I just want to give you a picture of what kind of a structure we can have for the pole set. Like this is a popular one, Z of X, the polynomial ring Z of X. So it has the minimum prime 0, and then at this level, all of those height 1 primes by the prime numbers or by irreducible polynomials. And then at level 2, you get those maximal ideals. Okay, this is the picture of the spectrum of Z of X. The big question was asked by Kaplansky in 1950s, and it is still open. Which partially ordered sets arise as spec R for some Newtonian ring R? Okay, what R can make the spectrum arise as a spec of R if you're given a pole set? And here there are a set of earlier results related to this question, like Huxter's characterization of the prime spectrum of a commutative ring as a topological space in 1969. And Jim Lewis of UNL's department chair, he had some result that every finite pole set is the prime spectrum of a commutative ring. That was in 1973. And there are some properties of prime spectrum of Newtonian rings by Mike Adam, 1974, and also Roger and Sylvia did something in 1976 and 2010. And there are also other characterizations of other specific classes of Newtonian rings. So I'm going to mention some of them later. And now let's come back to the question. This question is too hard, so we work toward a more modest goal, like describe pole sets arising from two-dimensional Newtonian domains related to polynomial rings. Can we characterize the spectrum of those rings? So characterize those, like, for example, this one, spectrum of Z of X, or Z sub P of X mod P, or Q of X, Y. Those are two-dimensional Newtonian domains. Specifically, Roger has a conjecture about this one. So, more general than this. So Z of X, Y, for example, mod of a height 1 prime ideal. You can generalize this to n variables mod n minus 2, n minus 1 height prime ideals. So how do we describe those spectrum? That's the question. Okay. And what do we need for characterization of the spec R? We need a list of axioms that describe the prime spectrum as a pole set, just property of the pole sets. And then we need to prove that any two pole sets satisfying these axioms are order isomorphic as partial order set. And maybe get some examples to show those pole set fitting axioms can be realized as a prime spectrum for some ring in the class. And here are this is the characterization of the spec Z of X by Roger Wiegand in 1986. I may be wrong with the year. There are two years, I'm not really sure. I'm going to, I think it's a 1986 paper. You have two of them. Yeah. So these are the 5 properties. I call it CZP properties for partially ordered set U. And this is actually the properties for spectrum of Z of X. First of all, remember the Z of X picture. This partially ordered set U is countable with a unique minimum element. For that case, is 0, it's the minimum. And U has dimension 2. I show you the 2 layers. And then every height 1 element of U is below infinite many height 2 elements. Every height 1 has infinite many height 2s about them. For every pair of distinct elements of height 1, there are only finite many height 2 elements above both of them. You take any 2 height 1, the top of these 2, you only have finite many of them. And then the crucial one is this condition, this axiom P5. If we take 2 finite subsets S and T, S is from the height 1, and T is from the height 2. Of course, not empty for S. And then there's a height 1 element, W, in the partially ordered set, such that whenever you have a maximal ideal, maximal ideal M greater than or above this W, whenever that's also above this one element in the height 1 element in S, then this M prime is forced to be in T. And this is a little tricky. I'm going to show you a picture of what does it mean. Let me go, the picture is later. Yeah, this is the picture, sorry, the wrong position. And so here, if the P5 is this, if you take 2 subsets, one from the height 1, one from height 2, and just think about the prime ideals, and this height 1 is not empty. So whenever we need to have one element W, existence of this element such that whenever you have height 2 prime, or maximal ideal is above one element from S and from W, then this element has to be in T. So that element is forced in T. P5 is the states that you have to, there exists such an element W. And I call that W radical element. So P5 states that there's such an element W so that whenever you have a height 2 prime above one of the elements in S here and W, then it has to be forced in T. That's the P5. So let's go back to these 5 axioms that Roger characterized. Any poset satisfying these 5 properties must be order isomorphic. That's his characterization. Okay, whenever you have this poset satisfying these 5 properties, the 2 of them must be isomorphic. So this is his theorem. Also regarding the spec Z of X, he showed that spec Z of X satisfies P1 through P5. And every partially ordered set which satisfies P1 through P5 and is order isomorphic to this spec. And then he made this conjecture, which is still open. We are still trying. The conjecture states that every 2-dimensional integral domain, which is a finitely generated Z algebra, has prime spectrum order isomorphic to spec Z of X. And here, 2-dimensional integral domain, which is a finitely generated algebra, has this form. It is like a Z of X1 through X and mod out a height n-1 prime ideal here. So you get a 2-dimensional integral domain, which is also a finitely generated Z algebra. The conjecture says the spec of this must be isomorphic to the spec of Z of X, and that is still open. So this is my definition, just define the radical element for that then. I'll pass that. Now the P5 can be changed to existence of a height 1 radical element for S and T. Now, a new question is we want to see for what integral domain A is this spectrum isomorphic to spec A. Okay. And the following range of domains have spectrum is already proved. These are the current results. Okay. This range, the following, the spectrum of this range are isomorphic to the spec of Z of X. One of them is D of X. D is an order in an algebraic number field. An order is an integral domain finite generated as a Z module with quotient field is an algebraic number field. Okay, this is in Rogers' paper, 1978. Another result is this K of XY, where K is an algebraic extension of a finite field. And that was proved the spectrum is the same as the spec Z of X in 1986 by Roger. And then this is Sylvia and I, we did a work for finite generated by rational extension of Z of X. So you're adding some quotient of the polynomials from the Z of X. And this will have the same spectrum as the spec Z of X. And another doctoral student of Sylvia's, Servo-Sadam, with Sylvia, they proved, this is 2005. I forgot to put in the year. And the spec B, where B is finite generated extension of D of X, containing the field of fractions of D of X with D being an order in an algebraic number field. So these are the current status, the domains we get that spectrum of them are isomorphic to the spec Z of X. And the next way, their other work will be working on other type of Euclidean rays. It may not have spec Z of X. They will have different spectrum, but we'll try to characterize them. So other type of rays, these are some work done with the like spec R of X, where R is a countable, semi-local, one-dimensional Euclidean domain. Both this 1 and 2, I think, is by I didn't put in here. Bill Hanser, Rothaus, and you, right? Or Lansing. Bill Hanser and you. I forgot to put in here. And this one is semi-local, one-dimensional Euclidean domain of any cardinality. So this is countable, and it's any cardinality, and it was improved by Chandy Shah also. So there are several papers on this. And then the power series range spec are with a double bracket of X power series. It's by rational extensions. For certain semi-local one-dimensional Euclidean domains, there are some results like Heinzer, Lantz, and Sylvia had 2 papers here, 1994 and 95. And with Servo-Sadam in 2001, there's another paper on Euclidean domains with the same prime ideal structure as Z localized 2 and X. So this is a related result. And then characterization of this for other type of rings, I'll just pass on this quickly. The prime ideals in polynomial and power series rings goes combined over Euclidean domains. And at the other doctoral students of Sylvia, Ella and Christina, they had a paper in 2014. And it's kind of a combination of the power series rings and polynomial rings like this. Okay, and still an ongoing project for this type of rings to categorize the spectrum of those rings, those statements. Yeah, right. It's right. I know. It is a really hard problem. Yeah. Yeah. And I want to quickly mention Sylvia had other part of work related to this topic by not putting it here. She had an earlier paper on maximal ideal space. Similarly, instead of looking at the spectrum, it's look at the set of maximal ideals. And also J-spec of Euclidean rings. J-specs, those prime ideals who are intersection of maximal ideals. Yeah, so it's kind of a narrow down a little bit. Roger And Sylvia had just this paper out, prime ideals in new theory rings or survey. So if any of you is interested in this topic, this is a very good paper to go. This is a survey paper. You can get most of the things from there. And this is it's a book series, right? That rings, I searched rings and module series. Springer. I think you search Google, you get it. So that's her prime ideal work. Okay, time. And then the last thing I want to talk about Sylvia's research is about the book she is writing with Bill Hanser and Crystal Rathaus. I think now it's 500 pages, right? I forgot to change. It's integral domains inside new theorem, power series rings, construction, and examples. And this is a quick description, the work of them on constructing interesting examples of new theorem and non-new theorem rings using completions. And you can see these kind of rings in the other work also, they touch that. So that's still, when it's going to finish? Soon, right? Yeah, I'm looking for it. So this is basically about the research of Sylvia Wiegand. Next, I want to take a little time to talk about her contribution to the community of women scientists, especially mathematicians. One fact I want to mention is for 17 years, Sylvia was the only female faculty in the math department of UNL. So the department chair, Jim Lewis, and Sylvia, they tried very hard to change the situation. And Sylvia was chairing a hearing committee. So within a few years, you got 4 women faculty, I guess. But someone left later. But that was a big effort. But now the department has over half women graduate students, I think. Yeah, more than half, right? And the department made a very, very big effort. And Sylvia was involved in many of those efforts, like Nebraska Math and Girls event and recruiting, this one I mentioned. And also there's a women's undergraduate conference each year. So she was involved in a lot of things in those. And also she was involved in AWM, of course, and served in many committees, also the president. And she also worked for ICWM. I don't know what committee, but some committees, and many more. So she was awarded the University of Nebraska's Outstanding Contribution to the Status of Women Award in 2000. And this is a picture with the former president of several of them, of AWM. And also, after 30 plus years, I want to say this is Susan Murray told me this, and a very, very tiny message, but I think it's good to see it. Susan told me that one of her classmates, like when she was in college, so maybe it must be more than 30 years ago. Yeah, okay, and that girl now is a lady. I think a few months ago you met her, right? Susan, yeah. So Susan met her and she remembered a new third lady. Yeah, who gave a seminar talk to her class. And she was amazed by the fact that women can also do high-level mathematics. It's very nice, and she's a non-math student. She does not have a math career, and so many years ago, she remembers as a new third lady. I think that women at those years, it's very few women give talks probably. So I think that's an inspiration for many girls your success. And this is a picture of Sylvia with women in Nepal. Women faculty and students, and you know that for the recent several years, she and Roger went to Nepal to help they developed the mathematics program, especially for women to do mathematics. They even was in the earthquake dangers. Yeah, and when they were having the conference. But I think that shows you put a lot of effort in encouraging women.
Yes, thanks for that invitation. We'll go back there again.
Yeah, and to me, Sylvia is a great advisor, a great leader, a role model for me, and she's my guide to Noether's family. So now I'm doing a commutative algebra, which is following Amy Noether's steps. And of course, she's a great mother, a great grandmother, a running partner. It has been very challenging. Now it's better. I think now I can. She's a tea lover. I want to add that she is also my thesis editor. I remember when I was writing the thesis, English is not my native language. When when she corrected my thesis, it was like nowhere is white, everywhere is red. Yeah, I remember those years was so difficult. Yeah, so I should add the editor also. This is from Serpil Sadam. She got her PhD in 1998, and she said something. There's something from last time, 2011, we had that AMS meeting, but there's something new too. And Serpil is an associate professor now, and interim dean at the College of Science, Engineering, and Technology at Texas Southern University. And she also talked about Roger. It's hard to forget him now because I spent countless hours to prove his conjecture. We are all trying to prove Roger's conjecture, still not successful. Yeah, but Sylvia's was known by her scones and brownies. I think that's also you're following the tradition of your grandmother. She told me yesterday her grandmother, Grace Chisholm Young, always have many mathematicians come to the house and she make cookies for them. So you are doing the same thing. Yeah. And I want to put up the Nick's slides from last time because he talked about the Sylvia's and something of. Oh, this is Marrow. Okay, Nick is later because the picture is Nick. And I didn't get contact with Marrow this time. This is from last time. I think I will pass. Okay, this is Christina Eubanks, a PhD in 2008, and Melissa Lucas. And Christina now is associate professor at there's a Loyola Marymount University, also director of a master graduate program. From Ella, here she lists a bunch of things, and this is a new picture I put up. Okay. And she's now a research assistant professor at West Virginia University. So she said Sylvia's algebraist advisor, chef of the great parties, expert traveler, mom, photographer, runner. And this is from Nick. Yeah, I want to put in this slide because Nick talked about Sylvia's brownies. With and no party event is complete without them. And then he also said something about Roger. Okay. Just remind you, last time you probably seen this. And one should always be looking for interesting eigenvalues from Roger. When near the weekends, one is always close to friendship, laughter, great conversation, and vast quantities of beautiful mathematics. I don't think I can finish my talk without talking about Roger because you're indecomposable. Right. And here, this is a slide from Graham. Last time, I really like it, so I put it here. This is a Roger's shower cap. Yeah, here Graham said some good words about it, and so we made a summary of Roger's quotes. No beer, no math. And this is the kind of math that polite people don't do in public when doing a very technical proof. Of course, we can't divide by 0 because that's illegal in Nebraska. I think it's illegal everywhere. Choose a real number r so that it is larger than 2 to the RT, I think, t, which we can do unless t is really big. And this is the interesting eigenvalues. And Roger reason Graham named it. That's a picture of, I don't remember where it's at. Sylvia is here, Roger is there. He's at the top. Okay, Roger and Sylvia, you're the greatest advisors. And I have this two as gift to you, but you need to prove a theorem to get it. Roger, you are the greatest I cannot see advisor ever. No beer, no math. And here is Sylvia, you are the best advisor. And have your New Zealand tea here. This is a tea bottle. And the other day here, we were talking about Roger saying about no beer, no math. But David Jorgensen was against it. He said it should be no math, no beer. And Roger responded with, more math, more beer, or more beer, more math. And I would say to Sylvia, no tea, no math. Okay, lastly, I want to thank for the organizers for giving me the opportunity, and you are all here. And also, Sylvia and I were enjoying the coconut in the zoo the other day. Thank you very much. Question? No question, no math.
Lots of math. Remarks, comments, historical remarks. I have a question. I think in the US you say ME letter and write AMY.
No,
EMY.
it is
But
EMY.
okay.
Oh, Amy, I was wrong.
No, I thought this was.
I was,
right
yeah,
here.
EMMY, right.
I'm going to explain why I thought it was okay, because the original birth name is Amalie.
Oh,
So it could be that someone tried to.
I need to
join
correct
Amalie
that,
and
yeah.
Amalie.
That's true. I didn't catch that.
So that was my remark.
Oh, great, great. We need to find that, correct it.
People would know what was meant.
Amy knew
so I
her.
didn't say anything, but I probably just as well to clarify that.
I shouldn't get that wrong.
No, it's okay.
Because she's not also, she's also my role model. I shouldn't get that wrong. Yeah. Any other questions?
Any other nasty remark?
Yeah.
I'm curious to know what is the maximum height they stay while going to Mount Everest.
Maximum height. Ooh.
Oh, I went to Kalapata, which is about, what, 18,400 feet, something like that.
I did not go quite that high. But we were
18, 18 floors, yeah.
Maximum height of the mountain they climb.
So it's about what? 57, 5800 meters, something like that. That was just last year.
we did not go to the top.
In Nepal?
Yeah, but you
Oh,
went
that
to
was
the
in
base
Nepal.
camp.
Well,
No, we
went
didn't
to
go.
the top.
You didn't
Well,
go.
Roger went to the top.
I looked down on Everest Base Camp from Kalapata. So that's what makes I think,
Some of the
no,
pictures.
I think that was probably from just below Namche Bazaar, wasn't
Yeah,
it?
that
It's a
one.
nice view, the first view you get of Everest is, about, 45 minutes to an hour below Namche Bazaar, and
And
you
our
happen to
friend,
get that picture there, I think.
our friend at JSC likes to take photos, as those of you who have met him know. And he has such a fancy camera that
Hmm.
has two lenses. So he can have one projecting in the background and making it look closer than it is, and another one capturing the closer image. So it didn't quite look like that. It's a little bit exaggerated, but still, it's a very nice photo.
They climbed also the mountain in Peru.
Yes.
Oh, Peru? Mm.
Yeah, that, well, let's see, I was, my, on my webpage, the picture there is on Nevado Chinche, which is 20,400 feet.
Wow.
That was back when I was a little younger, 1969.
I cannot match that.
Okay, anybody else? About climbing, etc. Okay, let's thank the speaker again.
Thank you. Thank you.